Okay, so now what we are going to look at is what is called the strongly connected components and weakly connected components of a directed graph. Okay, so what is a strongly connected component of a directed graph? So what it means is this. Let me use an example. So if this is the given directed graph, the graph could have one or more strongly connected components. So a strongly connected components is a subset, and actually the largest possible subset of vertices, such that they are reachable to each other using the edges of the directed graph. So in this directed graph, you see 1, 2, 4, and 7 could form a set of vertices such that they are reachable to each other. Say 1 is reachable, from 1 you can go to 2, and then you can also go to 7, and from 1 you can go to 4. Similarly, from 4 you can go to 2, then from there you can go to 7, and from there you can go to 1. From 2 you can go to 7, and then from 7 you can go to 1, and then also from there you can go to 4. From 7 you can go to 1, then to 4, as well as then to 2. So basically, from one vertex to any other vertex within that set you could go. So you have 1, 2, 4, 7, and you can go from any vertex in this subset to any other vertex using the edges and using the directed edges. So such a subset of the vertices is said to form what is called a strongly connected component. Now you could say 1, 2, 4 also satisfies the property. Because when I just say the subset is 1, 2, and 4, from 1 you can go to 2, and then also to 4, and then from 2 you can go to 1 and 4, and so on. But again, the word component always means you have to include the largest possible subset of vertices. So to this subset 1, 2, 4, if I add 7 to that subset, 7 also becomes part of the component in such a way that from any vertex you can reach any other vertex. But now you add one more vertex, say vertex 3 to this. So somebody asks, why can't 1 to 7 be called a component? Now they cannot be called a component because to this set 1 to 7, if I add 4 to this set, again all the 4 together, 1, 2, 4, and 7 are reachable to each other. So always we want the largest possible subset of vertices that are reachable to each other. So now to these 4 vertices, if I add one more vertex, say vertex 3, then if I consider 1, 2, 3, 4, and 7, these 5 vertices together, they are not reachable because from 3 you really can't go anywhere else in this directed graph. So that itself breaks the property. So when I say they form a component, from any vertex in the component you should be able to reach any other vertex. Okay. So what is that largest possible subset? So in this case 1, 2, 4, 7. So we can say they form a strongly connected component. Now what about the other vertices? So we can see 3 is one vertex, say in a set. We cannot add any vertex to this set. Say I cannot add 3 and 5 to be part of a subset where they are reachable to each other. No, because from 5 you can go to 3, but from 3 you cannot go to 5. So that means 3 itself is the largest possible subset of vertices that are reachable to each other. That's the only subset. That's the only set in that vertex in that subset. So we can say 3 forms a strongly connected component of its own. Similarly, with vertex 5, we cannot add any other vertex to the subset having vertex 5 because then the vertices in that subset are not reachable to each other. So for example, I cannot add 3 to it, or I cannot add 6 along with 5. 5 and 6 cannot form a strongly connected component because from 5 you can go to 6 but not from 6 to 5. So 5 is again on its own strongly connected component. Similarly, 6 is on its own strongly connected component. So that means this directed graph has 4 strongly connected components. Okay, so we are going to work out this example and actually going to find out the strongly connected components. I'm just trying to introduce what a strongly connected component means. Now, the directed graph could be given to you like this. Now, again, we can say after running the algorithm we're going to go through, we can say this 1, 2, 3, 4 form one strongly connected component because they're reachable to each other, and 5, 6, and 8 form one strongly connected component because they are again reachable to each other, and I cannot add any one more vertex to this subset of 3 vertices. So if I add 7 to this set, from 7 you can go to 5 and 8 as well as to 6, but I think from 5 you cannot go to 7. So that itself breaks the property. So that means 7 cannot be part of this subset. So 5, 6 and 8 which are reachable to each other form one strongly connected component. So that means 7 is on its own strongly connected component. Now you could have a graph where all the vertices could be part of just one strongly connected component. So you could have something like this also, as well as something like this where each vertex will be on its own strongly connected component. So all possibilities are there. Okay, so we'll go through these 4 examples to find strongly connected components. Now what is this weakly connected component? So that is something easy to figure out right away by looking at the graph. So let us look at this graph and then this graph. Now if you look at this graph, now if you remove the directions and just consider the undirected version of this graph, this is a connected graph because you can reach from one vertex to any other vertex in this undirected graph. So if you can reach from one vertex to any vertex in this undirected graph, then we can say the whole graph is one weakly connected component. On the other hand, in this directed graph, if you assign, again remove the directions, this is the undirected version. Now again, by applying the reachability criteria and the largest subset the criteria for a component, 1, 2, 3, 4 form one weakly connected component because that's the largest subset of vertices that are reachable to each other in the undirected version. Then 5, 6, 7, 8, these 4 vertices that are reachable to each other in the undirected version, again that's the largest subset of vertices that are reachable to each other, form another weakly connected component. Okay, so the weakly connected component means just consider the undirected version of the given directed graph and look at the set of vertices that are reachable to each other, the largest subset of vertices. So you could have again more than one weakly connected component in a given directed graph. So like in this case, you are given the whole thing of 1 through 8. These 8 vertices are said to form one directed graph, and this is the undirected version of that directed graph. We can say all the 8 vertices are part of one graph, but they are forming 2 weakly connected components. 1, 2, 3, 4 is one weakly connected component, 5, 6, 7, 8 is one weakly connected component. Now how to find weakly connected component? We all know the solution, just run depth first search, because once you have the undirected version, you can run depth first search, say in this case starting from 1 and see what vertices you can reach from 1. You could reach 2, 3 and 4. You could run also breadth first search, doesn't matter which one you run. Just find the vertices that are reachable to each other. So similarly, now we cannot reach 5, 6, 7, 8 by starting depth first search or breadth first search from 1 or 2, 3, 4. So you can reach only these 4 vertices in one instance of depth first search. So you have to start another instance of depth first search, say 5 from 5, 6, 7 or 8, and you could then find out you can reach the other 3 vertices. So we say these 4 vertices form another weakly connected component. On the other hand, in this undirected graph, you can start depth first search or breadth first search from any vertex, and you'll be able to see that you can reach all the other vertices. So we can say all these 7 vertices form one weakly connected component. Okay, so finding weakly connected component should be straightforward based on what we have seen so far, and even by visually looking at it, you will figure it out. So what we are now going to focus is how to find the strongly connected components of a given directed graph. So again, we are going to use depth first search. That means we are going to make use of a stack. Alright, so we're going to go through a two-step process. So please may follow through the process so it becomes easy to do the examples. Okay, so the first step is to run depth first search on the given directed graph. Now, as you run depth first search, you can keep track of the order in which the vertices were pushed and popped out. So for that, we will use a stack. Now, we will use another stack also. So we'll use two stack instances here. So we'll call one stack as a regular stack that we use to just keep track of the order in which vertices were pushed and popped out of depth first search. And then we'll make use of another stack called the SCC stack for strongly connected components to identify strongly connected components. So the regular stack will be used in the first step, and the SCC stack will be filled up in the first step and be used in the second step. So let us go through this example to find out how to use them. So first, start depth first search on the given directed graph. So start again. You can start from any vertex. We start with the lower ID vertex. So you push vertex 1 to the stack. So which is the regular stack. So you push vertex 1 to the regular stack, and that's the first vertex to be pushed. So from vertex 1, you can go to one of its outgoing neighbors, which we did this example just now, if you remember. So you go to vertex 2. So you push vertex 2 to the stack. Now we don't need to really worry about classifying edges as free edges and back edges and so on. So we don't need to focus on that. So let us just continue. So push vertex 2 to the stack. Now from vertex 2, you can go to vertex 7, which is not yet visited so far. So you push vertex 7 to the stack as the third vertex to be pushed. Now from vertex 7, you cannot go anywhere else to a new vertex because this outgoing neighbor 1 is already in the stack. So that should be called a back edge if you do the classification. So from 7 you cannot go anywhere else, so you pop out vertex 7, so that's the first vertex to be popped out of this regular stack. So remove vertex 7 from this regular stack. So as you pop out a vertex from the regular stack, push it to the SCC stack. So you're now popping out 7 from this regular stack, so you push it to the SCC stack. So 7 is the first vertex to be pushed to this SCC stack. So now the top of this regular stack is vertex 2. Now from vertex 2 you cannot go anywhere else. So it's time to pop out vertex 2 also from the regular stack. So that's the second vertex to be popped out. So again, as you pop out vertex 2 from the regular stack, you push it to the SCC stack. So now vertex 2 is pushed to the SCC stack. So now we are back to vertex 1 at the top of the regular stack. So from 1 you can now go to 3 or 4. So you go to 3. So you push 3 to the regular stack. So that's the fourth vertex to be pushed to the stack. Now from 3 you cannot go anywhere else. So you pop out vertex 3 from the regular stack. So now you push it to the SCC stack. So vertex 3 is now pushed to the SCC stack. So now we are back to vertex 1 at the top of the regular stack. Let me make sure I'm saving this. One second. Yeah. So vertex 1 is now at the top of the regular stack. So from vertex 1 you can go to vertex 4. Vertex 4 is the fifth vertex to be pushed to the stack. And from vertex 4 you cannot go 2 or 3 because you are already pushed and popped out. So they should be called cross edge. We just did this example. So now from vertex 4 we can visit vertex 6, which is not yet visited. So we push vertex 6 to the stack. So that's the sixth vertex we push to the stack. Now from 6 we cannot go anywhere else, so you pop out vertex 6. That's the fourth vertex to be popped out. So as you pop out the vertex 4 from the regular stack, you push it to the, we're popping out vertex 6. So as you pop out vertex 6 from the regular stack, push it to the SCC stack. So that means if vertex 6 is popped out from the regular stack, the top of the stack is vertex 4. So you are now at vertex 4. Now we cannot go anywhere else from vertex 4. 2 and 3 already visited, 6 is also already visited, so it's time to pop out vertex 4. So when you pop out vertex 4, you push it to the SCC stack. So now the top of the regular stack is vertex 1 again. Now from vertex 1 you cannot go anywhere else, so it's time to pop out vertex 1. So that's the sixth vertex to be popped out. So you push vertex 1 to the SEC stack. So now the top of the stack is empty, of the regular stack is empty. But you see, you started with 1 and you are able to go to 1, 2, 7, then 3, 4 and 6. So that's one instance of depth first search that we were able to do. So but now still vertex 5 is not visited. So you have to run a new instance of depth first search, a second instance of depth first search starting from 5. So push 5 to the regular stack. So that's the seventh vertex to be pushed to this regular stack. And now from 5, you have two outgoing edges to 3 and 6, and we saw that they are 3 and 6 are visited in an earlier instance of depth first search. So they should be cross edges. So you can't go anywhere else from vertex 5. So you pop out vertex 5 from the regular stack. And that's the seventh vertex we popped out. So you push it now to the SEC stack. So that's the first step. You run depth first search on the given directed graph and make use of the regular stack to just keep track of the order in which vertices are pushed and popped out. And as the vertices get popped out of the regular stack, push them to this SEC stack. So this is now the SEC stack with vertex 5 on the top of it. Okay. So now for the second step, what we need to do is reverse the directions of the edges in this given directed graph. So in the given graph, there's an edge from 1 to 2. So what I'm going to do is now build a new graph called G prime, and for this G prime, all you're going to do is just change the directions of the edges in the given graph. So we are going to have edge now from 2 to 1. They originally had from 7 to 1. On G prime, we're going to have from 1 to 7. So that's what we're going to do. Just change the directions of the edges. Now we have this reverse graph G prime. Now what we are going to do is run depth first search again on G prime on this reverse graph. Now we are not going to start depth first search from any arbitrary vertex. We are going to run depth first search in a certain order. So from which vertex we are going to start depth first search on this reverse graph? We are going to start from the vertex that is the top of this SEC stack. Now we may not be again able to visit all the vertices in this reverse graph in one instance of depth first search. So we'll start from the vertex that is in the top of the stack and see how far we can go. And if you're not able to visit all the vertices, you'll run again another instance or few more instances of depth first search on the reverse graph. We all know that in a directed graph we may be required to run more than one instance of depth first search if all the vertices are not reachable in the one instance. Alright, so we'll start with vertex 5, which is in the top of the SEC stack. So now to go through depth first search on this reverse graph, we could use again a regular stack just to see in what order in which we are going pushing and popping. I'm not going to illustrate that. So I'm going to just write the push and pop order to keep track of the vertices that are visited. So start from vertex 5, push it to the stack. That's the first vertex we push to the reverse to the regular stack that we can make use of to go through the process. Again, I'm not writing that down, so I just keep track of things like this. So push 5 to the stack. Now from 5 you cannot go anywhere else in this reverse graph. So that means you have to right away pop out vertex 5. So that's why I pop out vertex 5 right away. That's the first vertex we popped out of the stack. So that means, and also from the SEC stack, when you start depth first search, you should pop out the vertex. So after this instance of depth first search, we have the SEC stack looking up like this. Okay, so that is, we can say, one iteration of the second step. So that means one instance of depth first search. So what we need to do now is, before we begin the next instance, another instance of depth first search, which is called as the second iteration, remove the vertex that we have already processed. So in this case, we have just processed vertex 5. So remove vertex 5 and all the edges associated with vertex 5. So with vertex 5, we have just these two edges associated with it. So remove vertex 5 and the two edges associated with it. So this is now the new reverse graph without the vertex 5 and its edges. So Now on this new reverse graph, run depth first search again. From which vertex? Look at which vertex is now on the top of the SCC stack after the first iteration. So this is now on the top of the SCC stack, vertex 1. So start from vertex 1. You could continue the push and pop order. So you are going to push vertex 1 to the some regular stack you're using for just doing depth first search. So that's the second vertex to be pushed. So from vertex 1, you have an outgoing edge to 7. So you can push vertex 7 to that stack. So that's the third vertex to be pushed. Then from 7, you can go to 2. So that's the fourth vertex to be pushed. Now from 2, you can go to 4. That's the fifth vertex to be pushed to the stack. Now from 4, now again, earlier from 2 you cannot go to 1 because 1 is already in the stack. We all know that from depth first search. So you have to go to 4. Now from 4 you have again a back edge to 1. So you cannot go to 1. So you cannot go anywhere else to a new vertex from 4. So that's the time to pop out 4 from that regular stack. So that's the second vertex to be popped out. We're continuing the push and pop numbers. So that's second vertex to be popped out of the stack. So back to vertex 2 at the top of the stack. So now you're removing also 2 because you don't go anywhere else from 2. So you pop out vertex 2 and then back to 7. You can't go anywhere else. So pop out 7. Then back to 1. You can't also go anywhere else from 1. Pop out 1. So in this iteration or instance of depth first search, we started from 1 and you're able to visit 1, 7, 2, 4. So note down those 4 vertices that you are able to visit. So this set of vertices that are able to visit is said to form one strongly connected component. Similarly here 5 is said to form one strongly connected component of its own because that's the vertex we are able to visit starting from 5. So in each iteration in the second step we are running depth first search and we're basically finding what set of vertices are forming one strongly connected component. So the vertices that are reachable in this iteration of depth first search are 1, 7, 2, 4. So they are said to form one strongly connected component. Okay. So now what we do is we also remove 1, 7, 2, 4 from this SCC stack. So we go through the process of removing those specific vertices to the SCC stack, and after we do that, this is how the SCC stack looks like with just 6 and 3. So after 1, 7, 2, 4 are removed, we have just 6 and 3. Now also you should remove the vertices and their associated edges from the given graph. So we were here. So remove 1, 7, 2, 4, which means all those edges will go away associated with 1, 7, 2, 4. So after we go through that removing process, we'll be just left with 3 and 6 like this with no edges. You can cross check if all these edges are. So you should remove any edge associated with that vertex. So with 4 you have outgoing edge as well as some incoming edges. So you should remove all the edges associated with vertex 4. So all these edges will go away. Similarly for 2, these two outgoing edges as well as this incoming edge will go away. So when you follow this procedure, this is what we're going to end up with, just with vertices 3 and 6. So we can still call them as a graph. So run now a third instance of depth first search as a third iteration on this reverse graph starting from 6. That's the top of this SCC stack now. So start with 6, push 6 to the stack. We can't go anywhere else from 6, so pop out 6. That means 6 is on its own strongly connected component. So now remove 6 from the graph. We are left with just 3 in the reverse graph. So start depth first search from 3. So push 3 as well as pop out 3. So that's now on its own strongly connected component. So now on the original graph, as you go through the iterations, you can mark down the vertices that form a strongly connected component. So at the end of the first iteration, we found vertex 5 to be a strongly connected component of its own. At the end of the second iteration, we found vertices 1, 2, 7, 4 form a strongly connected component. Then at the end of the third iteration, vertex 6 on its own strongly connected component. At the end of the fourth iteration, vertex 3 is on its own strongly connected component. So these are the 4 strongly connected components of the given directed graph. You can again always cross check whether the vertices are reachable to each other if we have more than one size strongly connected component. Like here, 1, 2, 7, 4 should be reachable to each other. Okay, so this is how you find a strongly connected component or all the strongly connected components in a given directed graph. Okay, so let me just stop this video and save it, and I'll come back and we'll do the other examples.